Hey, I want to talk about a special type of sequence known as a geometric sequence. Consider this sequence here, 10, 30, 90, 270, etc. And it's not hard to see that each term is 3 times the term before it. We could write it recursively as a sub 1 equals 10, and then each term is 3 times the term before it. A sub n is 3 times a sub n minus 1 for each n greater than 1. And if you look at this rule for finding the general terms of the sequence after the first term, we get that if you divide a term by the term before it, you get this constant 3, and that's for any pair of terms starting with the first one. And when this happens, we call a sequence geometric. In other words, if the ratio of any term to the term before it is constant any place in the sequence, the same constant, then the sequence is geometric. This is a geometric sequence with the ratio r equal to 3. And for this particular sequence, if you factored out a 10 from each term and wrote it as 10 times the sequence 1, 3, 9, 27, 81, etc., it becomes clear that the general term of the sequence, or a formula for the general term of the sequence, is 10 times 3 to the n minus 1, where n starts at 1 and goes to infinity as usual. And we can do this with any geometric sequence, giving rise to the idea of there's a general form of a geometric sequence, and it's some number times r to the n minus 1 as n goes from 1 to infinity, where the sum number a, in this case, is always the first term of the sequence, because when n is 1, r to the 1 minus 1 is r to the 0, which is just 1, and so the first term is just a. So that a is really a sub 1, or the first term, and then it's times increasing powers of r. And you'll sometimes see this written as a times r to the n as n goes from 0 to infinity, because as n goes from 1 to infinity, n minus 1 goes from 0 to infinity. So there's two different ways of writing the same thing. Let's make a little room. There will be times when it will be very useful, given a geometric sequence, to rewrite it in terms of the general form. So take these two geometric sequences and see if you can't rewrite them in their general forms. And all that's really required is determining what the first term is and determining what the ratio r is. So take a moment, pause the video, and see if you can rewrite these two sequences. For the first one, you should have gotten 3 times negative 4 to the n minus 1 as n goes from 1 to infinity, or if you prefer, 3 times negative 4 to the n as n goes from 0 to infinity. It's the same thing, but the first term is 3, and the ratio r is negative 4. Any term divided by the term before it is always negative 4. And similarly, this second sequence is 100 times 1/10 to the n minus 1 as n goes from 1 to infinity. Take any term, divide it by the term before it, and you clearly get 1/10. Okay, take any sequence, whether it's geometric or not. We define something called the nth partial sum of the sequence, s sub n, as simply the sum of the first n terms of the sequence, a sub 1 plus a sub 2, etc., all the way up through to plus a sub n. This is very often written in what we call summation notation. This simply says the sum as I goes from 1 to n of a sub I. And all it means is exactly the expression on the left. It means a sub 1 plus a sub 2 plus a sub 3, all the way up through a sub n. Okay, suppose we have a geometric sequence, any geometric sequence, a times r to the n minus 1 as n goes from 1 to infinity, which is simply the sequence a times r squared, a times r cubed, etc. Notice that each term is r times the term before it. Then the nth partial sums are s sub 1 is equal to a, s sub 2 is equal to a plus a times r, s sub 3 is a plus a times r squared. And in general, the nth partial sum of a geometric sequence is a plus a times r squared, etc., all the way up to a times r to the n minus 1. Now, take that equation and multiply both sides by r, and you get that r times s sub n is a times r plus a times r squared plus a times r cubed, all the way up to a times r to the n. The powers of r have each increased by 1. Now, look what happens when we subtract s sub n, this expression here, from r times s sub n, this expression here. Well, the a times r right here minus the a times r here, that's a 0. Similarly, a times r squared minus a times r squared is 0. And there's an a times r cubed here and an a times r cubed somewhere in there, and that gives you a 0. And all the terms cancel except, well, there's an a times r to the n minus 1 somewhere over here that cancels with this a times r to the n minus 1, meaning when you subtract you get 0. And the only terms that you're left with are this one right here and this one right here. And since we're subtracting that top expression, s sub n, from the bottom one, r times s sub n, we get that their difference is a times r to the n minus a. And now if we factor out s sub n on the left and factor out a on the right, we get this expression right here. And dividing both sides by r minus 1, this gives us a formula for the nth partial sum of a geometric sequence. For example, suppose we wanted to go back to our first geometric sequence that we looked at, 10, 30, 90, 270, etc. And suppose we wanted to add the first 20 terms of that sequence. The general form of the sequence is 10 times 3 to the n minus 1, as n goes from 1 to infinity. And so the 20th partial sum is 10 times 3 to the 20th minus 1, all divided by 3 minus 1. Which turns out to be some number over 17 billion. I don't claim that this formula actually made that computation any easier. It might be easier to actually add the first 20 terms than to compute 3 to the 20th. But still, we have a formula for the nth partial sum of a geometric sequence, and it will be very handy in the very near future. Okay, that was geometric sequences. There is no new homework on them. Don't worry, plenty of it to come. See you soon. Bye.